Hi class, how are you today? That's wonderful. The learning target for today is to be able to compute binomial distributions using the formula, a calculator, and a table. 3. You can compute binomial distributions using the formula, a calculator, and a table. 2. You can compute binomial distributions using the formula, a calculator, or a table. 1. You can identify the important parts of a binomial distribution. 0. You cannot identify the important parts of a binomial distribution. Let's get started. Section 5.2, Binomial Probabilities. Focus points. List the defining features of a binomial experiment. Compute binomial probabilities using a graphing calculator and a table. Use the binomial table to find P of R. Use the binomial probability distribution to solve real-world applications. Binomial experiment. On a TV game show, each contestant has a try at the Wheel of Fortune. The Wheel of Fortune is a roulette wheel with 36 slots, one of which is gold. If the ball lands on the gold slot, the contestant wins $50,000. No other slot pays. What is the probability that the game show will have to pay the fortune to 3 contestants out of 100? This problem has exactly 2 possible outcomes for each trial. Problems like these are called binomial experiments, or Bernoulli experiments, after the Swiss mathematician Jacob Bernoulli, who studied them extensively in the late 1600s, hence why they're called binomial experiments, because there's 2 of them. 2 possible outcomes. Here are the features of them. There's a fixed number of trials. We denote this number by the letter n. The n trials are independent and repeated under identical conditions. Each trial has only 2 outcomes, success, denoted by S, and failure, denoted by F. For each individual trial, the probability of success is the same. We denote the probability of success by P and that of a failure by Q. Since each trial results in either success or failure, P plus Q equals 1, and Q is equal to 1 minus P. So the probability that there's a success is P, the probability that there's a failure is Q. And of course, since those are the only answers, the only possible outcomes, their probabilities need to add to 1. The central problem of binomial experiment is to find the probability of R successes out of n trials. So what we're trying to do is we want to find a certain number of successes out of a certain number of trials. So if there are 5 trials, you might want to know what's the probability of getting 3 successes. That's what we're trying to do here. Let's see how the Wheel of Fortune problem meets the criteria of a binomial experiment. We'll take the criteria one at a time. Each of the 100 contestants has a trial at the wheel, so there are 100 trials in this problem. Assuming that the wheel is fair, the trials are independent, since the result of one spin of the wheel has no effect on the results of the other spins. We are interested in only 2 outcomes on each spin of the wheel. The ball either lands on the gold or it does not. Let's call landing on the gold success and not landing on the gold failure. In general, the assignment of the terms success and failure to outcomes does not imply good or bad results. These terms are assigned simply for the user's convenience. So if we wanted to, we could call landing on the gold a failure and landing not on the gold success. It's just up to whatever we want to do. On each trial, the probability P of success landing on gold is 1 out of 36, since there are 36 slots and only one of them is gold. Consequently, the probability of failure on each trial is 35 out of 36, because it's 1 minus the probability of success. So probability of failure is 1 minus the probability of success. The complement, as it were. We want to know the probability of 3 successes out of 100 trials. So in this example, it turns out that the probability the quiz show will have to pay the fortune to R equals 3 contestants out of 100 is about 0.23. Later in the section, we'll see how this probability was computed. Computing probabilities for a binomial experiment using the binomial distribution formula. The central problem of a binomial experiment is finding the probability of R successes out of n trials. Déjà vu. Suppose you are taking a timed final exam. You have 3 multiple choice questions left to do. Each question has 4 suggested answers, and only one of the answers is correct. You have only 5 seconds left to do these 3 questions, so you decide to mark answers on the answer sheet without even reading the questions. Assuming that your answers are randomly selected, what is the probability that you will get 0, 1, 2, or all 3 questions correct? This is a binomial experiment. Each question can be thought of as a trial, so there are n equals 3 trials. The possible outcomes on each trial are success, S, indicating a correct response, or failure, F, meaning a wrong answer. The trials are independent. The outcome of any one trial does not affect the outcome of others. What is the probability of success on any one question? Since you are guessing and there are 4 answers from which to select, the probability of a correct answer is 0.25. The probability Q of a wrong answer is then 0.75. So, correct answer 1/4, incorrect answer 3/4, the difference between them. In short, we have a binomial experiment with n equals 3, p equals 0.25, and q equals 0.75. So these were some of the important parts I was talking about in the learning target. Knowing what different variables represent. N being 3 is the number of trials, p being 0.25, the probability of success, and q being 0.75, the probability of failure. There are 8 possible combinations of S's and F's. They are there. To compute the probability of each outcome, we can use the multiplication law because the trials are independent. So the probability of SSF, success, success, and then failure, would be multiplying those 3 things together. Probability of a success, probability of a success, probability of a failure. So as we said, probability of success is P, probability of failure is Q. So it's P times Q, or in this case, P squared Q. So 0.25 times 0.25 times 0.75, which is about 0.047. So the probability of 2 successes and then 1 failure, in that order specifically, is 0.047. Now if we want to find all the probabilities, we have this nice little table. So in this table, we have the one we were just talking about, probability of success, success, failure, which is computed this way, but you get all of them. Notice that the ones that have 2 successes and 1 failure are all the same. The ones with 2 failures and 1 success, also all the same. And then probability of 3 failures is just cubing 0.75. Probability of 3 successes is just cubing 0.25. And R is another important part that you need to know because that's the number of successes. So when we're trying to figure out the number of successes, that's R. So it differs on what you're asking for. Now we can compute the probability of R successes out of 3 trials for R equals 0, 1, 2, or 3. Let's compute P of 1. The notation P of 1 stands for the probability of 1 success. For 3 trials, there are 3 different outcomes that show exactly 1 success. They are the outcomes SFF, FSF, and FFS. Since the outcomes are mutually exclusive, we can add the probabilities. So probability of 1 success is adding up those 3 probabilities, which was p2 squared plus p2 squared plus p2 squared, because if you go back to the original, the three that had one success were each 0.141. So we just add these three. Add the three together, and we get 0.422. In the same way, we can find p of 0, p of 2, and p of 3. These values are shown in this table. So probability of 0 is just q to the third. Probability of 1 is the probability of each of these three, which were pq squared, added together. So 3pq squared. Probability of 2, again, adding these three up, 3p squared q. And probability of 3 successes is just p cubed. Formula for binomial probability distribution is p of r equals n factorial over r factorial times n minus r factorial times p to the r q to the n minus r, or combinations of n and r, or n choose r, times p to the r times q to the n minus r. This might look familiar to anyone who has dealt with binomial expansions. If you're squaring a binomial, cubing a binomial to any power, you may have worked with this stuff before. It's seen a lot in pre-calc. You might have seen it in algebra too. So n is the number of trials. P is the probability of success on each trial. Q is 1 minus p, the probability of failure in each trial. R is the random variable representing the number of successes out of n trials. These, again, are all the important parts, n, p, q, r. Factorial notation we've talked about. It's just take the number, multiply by all the numbers before it. And combinations, or n choose r, that's the way it's said, but it's combinations of n and r. We've also talked about back in Chapter 4. Privacy is a concern for many users of the internet. One survey showed that 59% of internet users are somewhat concerned about the confidentiality of their email. Based on this information, what is the probability that for a random sample of 10 internet users, 6 are concerned about the privacy of their email? This is a binomial experiment with 10 trials. If we assign success to an internet user being concerned about privacy of email, the probability of success is 59%. We are interested in the probability of 6 successes. So, n is 10, p is 0.59, q is 0.41, which was, again, 1 minus 0.59, r is 6. So, by the formula, we do 10 choose 6, which becomes 210, times 0.59 to the 6th, times 0.41 to the 10 minus 6, which is 4. Then figure those out, multiply them all together, and it approximates to about 0.25. So there is about a 25% chance that exactly 6 out of 10 internet users are concerned about the privacy of email. Many calculators have a built-in combinations function on the TI-84 Plus, TI-83 Plus, TI Inspire with TI-84 Plus keypad. Calculators press the math key and select PRB. I believe that's the fourth section to the right, or you just press the left button if I'm correct, after you get to the math key. The combinations function is designated NCR. N choose R is what it stands for. This display here shows how to compute it. You do N or you do 10 in this case, which is whatever n is. You go to the math button, you find NCR, you put that in, then you press sit. So it's 10, choose sits. Then you multiply it by p to the r, so 0.59 to the sixth, and you multiply that by q to the n minus r, or 0.41 to the 10 minus 6. And you get about 0.25, 0.03034245, or we just rounded to 0.25. So that's a different way to calculate it. You can do it by hand, or you can just plug all that into your calculator. Using a binomial distribution table. In many cases, we will be interested in the probability of a range of successes. In such cases, we need to use the addition rule for mutually exclusive events. For instance, for n equals 6 and p equals 0.5. Probability of 4 or fewer successes is the probability of r is less than or equal to 4, which is equal to the probability that r equals 4, or 3, or 2, or 1, or 0. So, or means add. So, probability of 4 plus probability of 3 plus probability of 2 plus probability of 1 plus the probability of 0. It would be a bit of a chore to use the binomial distribution formula to compute all the required probabilities, though if you wish you can do it. Table 3 of Appendix 2 gives values of p of r for selected p-values and values of n through 20. To use the table, find the appropriate section for n and then use the entries in the columns headed by the p-values and the rows headed by their r-values. I'll show you how to do this in class so we can specifically look at the table, but here is just an example of what part of the table looks like and how to use it. Table 510, the one below, is an excerpt from Table 3 of Appendix 2, the one in your book, showing the section for n equals 6. Notice that all possible r values between 0 and 6 are given as row headers. The value p equals 0.5 is one of the column headers. That's the one highlighted in pink. For n equals 6 and p equals 0.5, you can find the value of p of 4 by looking at the entry in the row headed by 4, which is labeled in yellow, and the column headed by 0.5, again in pink. Notice that p of 4 is 0.234. So if you're looking for an r of 4 and a p of 0.5, you just find the intersection of the two, which in this case is 0.234. Likewise, you can find other values of p of r from the table. In fact, n equals 6 and p equals 0.5 has p of less than or equal to 4, so you find the probabilities of 4, 3, 2, and 1, and 0, which are in the column in pink. See 0.16, 0.016, 0.094, 0.234, 0.312, and 0.234. So you add those all up, and you'll get 0.890. Alternatively, to compute probability of r is less than or equal to 4 for n equals 6, you can use the fact that the total of p of r values for r between 0 and 6 is 1 and the complement rule. Since the complement of an event r is less than or equal to 4 is the event r is greater than or equal to 5, we have probability of r is less than or equal to 4 is 1 minus p of 5 minus p of 6. So instead of getting all 5 of those values before, just do 1 minus those 2 values, and you'll get 0.89, the same thing we got before. A biologist is studying a new hybrid tomato. It is known that the seeds of this hybrid tomato have probability 0.7 of germinating. The biologist plants 6 seeds. What is the probability that exactly 4 seeds will germinate? This is a binomial experiment with n equals 6 trials. Each seed planted represents an independent trial. We'll say germination is a success. So the probability of success on each trial is 0.7. So we've got n equals 6, p is 0.7, q is 0.3, and r is 4. We wish to find p of 4, the probability of exactly 4 successes. In Table 3, it's Appendix 2, the table that we've been looking at. Find the section with n equals 6. So for some reason they still have the previous one highlighted. So we're actually looking at 0.7 now. But we are still looking for r equals 4. So where 0.7 intercepts r equals 4 is 0.324. So as we just did, find the entry in the column headed by n equals 6 and the row headed by p equals 0.7 and the row headed by r equals 4. This entry, as I said, is 0.324. What is the probability that at least 4 seeds will germinate? In this case, we are interested in the probability of 4 or more seeds germinating. This means we are to compute p of r is greater than or equal to 4. Since the events are mutually exclusive, we can use the addition rule. So add those 3 up, and we already know the value of p of 4, so we just need to find the probability of 5 and 6. Use the same part of the table, but find the entries in the row headed by the r value 5 and then the r value 6. Be sure to use the column headed by the value of p, 0.7. So again, back to the table. We found 4, 0.34, now we need 0.303 and 0.118 because those are 5 and 6. Now we have all the parts necessary to compute the probability of r greater than or equal to 4. So you add those 3 up and you get 0.745. Sampling without replacement, use of the hypergeometric probability distribution. If the population is relatively small and we draw samples without replacement, the assumption of independent trials is not valid and we should not use the binomial distribution. The hypergeometric distribution is a probability distribution of a random variable that has 2 outcomes when sampling is done without replacement. This is the distribution that is appropriate when the sample size is so small that sampling without replacement results in trials that are not even approximately independent. A discussion of the hypergeometric distribution can be found in Appendix 1. So that last part is kind of just a little different thing to add on. Now time for the sponge. In a Pokemon game, there is a 16% chance of encountering a Pokemon for each step taken in grass. I looked it up. To give yourself a good chance of getting good Pokemon, you plan to take 10 steps. You want to find the probability of encountering exactly 2 Pokemon. Now, there's a few things here. Mostly it's talking about the important things that I mentioned. First, what is a success and what is a failure? So just name both of those. Then, what is n in this case? Then, what is r in this case? Then, what is p? And then, what is q? Again, in this case. F, set up the formula to find the probability. And then G, find the probability. So it's doing it step by step what you need to do. Alright, that's it for this lesson. Once again, please make sure to take notes on the entire lesson. Attempt the sponge. Gotta attempt it. I actually don't think this one is too bad, even though this stuff seems difficult. I think this sponge is easy enough to do. Please make sure to take a picture of everything, submit it all to Google Classroom, and have a good night.